All right, so today we're going to be discussing something a little interesting about thermodynamics, and it's called the three laws of thermodynamics. You notice how these things always come in threes, right? You have Newton's three laws of motion. Kepler had a few three laws of orbital motion. These things just kind of come in threes. I think we just like threes. So this is the three laws of thermodynamics. And this is all talking about heat and how heat can flow from hot to cold and how much work we can do out of it. So let's just get started into it. So we have the first law. First law, I like to call it is you can't win. Basically, what this says is that there's the change in energy of a system, whatever system it happens to be, some gas, whatever, is equal to the amount of heat added plus the amount of work done. So if you do work on a system, then that can increase the energy. We've talked about this before in the last unit on energy. It was called the work energy theorem, right? You can do work to increase or decrease the energy of a system. So what this is saying is that the total energy, and we're going to call this the internal energy, is equal to the amount of heat, and this is the change. The change in energy is equal to the amount of heat given to the system plus the amount of work done on the system. Now, work is something interesting where in this scenario, we can actually have work to be positive or negative. Okay, positive or negative. A positive work is when you're doing work on a system where you increase the energy there. Okay, the work done by a system would actually decrease the amount of energy. You're expending energy to do work. So work can either be positive or negative. You can have a positive change in energy or a negative change in energy. The same thing can be said about uh, heat. Okay, heat can either be taken from the system or given to the system. So in reality, both of these can either be positive or negative, and depending on those changes, you end up with a positive or negative change in energy. But what the bottom line is for that right there is that right down here, it says you can't get more out than what you put in. So the amount of energy that you get, the amount of change in energy that you get from a system can only equal the amount of heat you put in plus the amount of work you put in. You're never going to get any more than what you put into the system out of it. So let's say you do work on it and you give heat to the system, so you've inputted some energy. Well, if you have a capability of getting that energy back out, you're not going to get more out than what you put in. Okay, and that is law number one. This is really just a restatement of conservation of energy. It's just a restatement of conservation of energy. That's all the first law is. Okay. Just remind you that you can pause the video if you need time to copy this down if you're taking notes, or if I'm just going too fast, you can always rewind it and take a look at what I said again. So let's move on. So this is law number two. Law number two, I like to call is you can't break even. So what it says, no process is possible whose sole result is the complete conversion of heat from a hot reservoir into mechanical work. Okay, bottom line is you cannot attain 100% efficiency. So in the last slide, we saw that delta U is equal to the amount of heat you put in plus the amount of work that comes out of it. Okay. Now, what the second law says is that not only can you not get more, but this equality is actually not even equality. You can't get as much out as what you even put in. Okay, let's say you do some work on the system and you add some heat into the system. If you're expecting to get anything out, don't expect to get everything that you put into it out of it. There's no way that you can get 100% efficiency. Okay, how this might look is in something known as a heat engine. And a heat engine says, okay, you have a reservoir that's called the heat source, something that's at a high temperature. You have something called a heat sink, which is a low temperature. And in between those two things, you put an engine, something, and we'll talk about some examples of what a heat engine might look like. Okay, and what the heat engine does is it takes heat from the high temperature area, the heat source, and it does something with it. You might be able to get some of the work out, and then whatever work you or whatever can't be converted into work, gets thrown back into the heat sink. You can think about this as being the waste. Okay, this is waste heat. All right, so QH, theoretically, if you had a 100% efficient engine, QH would equal W, where all of the heat coming in, being energy, could be converted into work. The problem with it is that the second law says that can't happen. You're always going to have heat lost to, say, the environment or some other heat sink that is going to affect your efficiency. So the equation that we give to this is saying, okay, QH is going to be equal to QC plus W. Okay, really, this again is just a conservation of energy type statement, but it's just telling you that QH is not going to equal W. There's always going to be some value of energy wasted by this engine. Okay, and a heat engine can be something like the engine in your car. I mean, you can think about an engine. It does not create heat. A heat engine doesn't create heat, but it uses heat to do something with it. Okay, in your car, it uses the ignition of gasoline to power to move the pistons and things like that. So it uses heat. But if you've ever noticed, if you've run your car for too long or for just a while, the whole engine, the hood, and everything is really, really hot, and that is all because of this waste heat. Okay, if we had a more efficient car engine, the engine itself wouldn't heat up as much, and more of that heat would be involved in work. You'd have better gas mileage. Okay, and the last one is it is impossible to reach absolute zero, and I like to call this as you can't get out of the game. So not only can you not break even, you do not have the ability to get out of the game. Okay, if you had the ability to get down to absolute zero, then you think about this. If we go back, absolute zero would be, say, the low temperature here, QC, would be equal to zero, and that would end up being QH is equal to W, and that's something that we can't have according to the second law. Okay, so it is impossible to reach absolute zero. And then we throw this word in here. You might recognize that word. This is called entropy, which basically means chaos or disorder. The law number 3 says that entropy only increases, it never decreases. If you end up with a situation where something becomes more ordered, okay, all that means is that in the local area, entropy might decrease. But in general, for the entire universe, entropy increases. Okay, let's talk about this in terms of, say, some water. Okay, in a box that is heated up, you have a whole bunch of water vapor. Okay, and all these particles are just moving around. They're all over the place. They're going, zipping around. This is something that has a very high entropy to it. Okay, now let's cool it down. Let's cool it down. So it gets to a point where the molecules have less and less energy, and they're able to coalesce into a liquid. Okay, so what's going on? Entropy is actually decreasing. Something is getting more and more ordered. Okay, and if we actually cool it down even more, you would end up with a situation where you had a solid block of ice sitting here in the bottom of the box. Okay, again, entropy decreases as you go from gas to solid. Okay, we can know that we can't keep ice there for that long. It heats back up, and as it goes back to a gas, entropy actually increases. Okay, so it's all just a matter of randomness or disorder. Entropy decreases if it gets more orderly, increases as it gets more disorderly. And the law number 3 says, hey, entropy is on the whole of the universe always, always, always increases as time goes on. Okay, and this is just some information about entropy, some of the things that we've already heard about or seen. The end of the universe, as entropy gets increasing, 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 the end of the universe is affectionately known as the heat death of the universe. Basically, what it means is that all matter is going to break down into its constituent particles, which are then going to break down and just at the very end of the universe, it's going to be all chaos and randomness. There's not going to be any order to anything, which means there's not going to be any solid matter left over. Now, you don't necessarily need to know that, but that's just an implication of entropy. So think about it in your own household. If you're in your own room, As time goes on, does entropy increase or decrease? I would probably venture to say it probably increases for a while until someone says, hey, clean your room, and then it might actually decrease. All right, so that is the 3 laws of thermodynamics. I'm also going to post another short little entertaining video that I suggest that you watch. It has some good information in there, but it is pretty entertaining. So until next time.